Welcome students once again, IIT PAL lecture series, lecture number 5 on logarithms. Today we are going to, this will be the last lecture in the series of logarithms. So today we are going to solve some advanced problems on logarithms, which will ensure that you have understood all the properties of logarithms correctly. Okay, so let us try to solve more advanced problems today. So the first problem is prove that log to the base 34 of 5 lies in the open interval 1 by 3 to 1 by 2. Okay, this is the question. Now how will you approach this question? First we will write it mathematically. This is to prove 1 by 3 is strictly less than log to the base 34 of 5, which is less than 1 by 2, right. Can I solve it directly? Yes, I can, but let me make it into two parts. So let us take the first part. Let me change the color. Let us use this part separately and this part separately. That means what I am asking is, I have to show 1 by 3 is less than log to the base 34 of 5. At the same time, I have to show log to the base 34 of 5 is less than half. Okay. In order to prove this, how we will proceed? This is, I am just modifying what is to be proved. Right. So this is one part and this is that other part. So what essentially it means is, I can multiply both sides by 3, then I will get log to the base 34 of 5, log to the base 34 of 5, and here I will multiply both sides by 2, then I will get log to the base 34 of 5 less than 1. Now do you remember any law which I can use over here and here? We can use a power law, right. So if we can use a power law, what will happen? Just remember what is a power law. N times log to the base a of m is equivalent to saying log to the base a of m raised to n. This is the power law. Right. So I will use this law here. So now I am looking at this log term with reference to 1 on the number line. Okay. So this simply means, that is, they are asking us to prove 1 less than log to the base 34 of 5 raised to 3, and on this side again I can use a power law here, and they are asking us to prove log to the base 34 of 5 square is less than 1. Now our job is whether this is true or not. Okay. Do I know something about this? How can I represent this 1? Yes, I know, because we know log to the base a of a is equal to 1. We have proved this property. Whenever, obviously, we have some conditions, a is greater than 0 and a is not equal to 1. So we want to use this property in order to prove this particular term. So what we are saying then is, log to the base 34 of 34, is it less than log to the base 34 of 5 cube? What is 5 cube? It is 125. Right? And I am asking a similar question here, log to the base 34 of 25 is less than log to the base 34 of 34. Okay. Now what do you say about this? You know log is a monotone function, or if we have already seen this property, if m is less than n, then it is true that log to the base a of m is also less than log to the base a of n. This property we have already derived in previous lectures. That means what? Now I am having, instead of m I am having 34 here, instead of n I am having 125 here. If this is to be true, then I should have this relation between m and n, right. So, is 34 less than 125? If I want to use this relation, this property, then we will say log to the base 34, this a can be 34 of 34 less than log to the base 34 of 125, right. So, I am just converting this property with appropriate enumerations. A is 34, m is 34 here, and n is 125 here. 34 is less than 125. So, now we will look for this particular term. So, in particular you must have understood that because 34 is less than 125, I have log to the base 34 of 34 less than log to the base 34 of 125, and therefore, all previous steps will go through, and I have proved 1 is less than 3 times log to the base 34 of 5. Okay. Now, our job is to show this particular quantity, but if I want to show this particular inequality, then it is equivalent to showing this particular inequality. Once I have this inequality, again I will use the same rule, m less than n if and only if log to the base a of m is less than log to the base a of n. So, essentially I am asking a question, is 25 less than 34? If it is so, then log to the base 34 of 25 will be less than log to the base 34 of 34, right. This is by default true, therefore, this inequality is also true, and because this inequality is true, our original inequality is also true. Therefore, we have shown that 1 by 3 is less than log to the base 34 of 5, which is less than 1 by 2. This is what we wanted to prove. Just go through once. 1 by 3 less than log to the base 34 less than half. I hope this is clear. Now, you should be able to solve any problem on this of this kind. Let us now take little bit advanced problem which deals with summation. So, this problem is, let us call it problem number 2. Let me use a different marker, slightly bigger marker. Okay. So, this problem is, show that let us go up, show that summation over r is equal to 2 to 45 1 upon log to the base r of n is equal to log to the base n of 45 factorial. I assume you know this notation factorial, but if you do not know, let me just tell what is this notation. If I want to write m factorial, this is nothing but m into m minus 1 and so on into 2 into 1. Okay. This is the m factorial notation mean. Okay. Now, first observe this problem. You just see r is the base, here n is the base. Okay. So, in the left hand side the base is different. If I want to apply any rule that I know, first of all I should get the same basis. If I do not have the same basis, only one formulation that will come to my help is change of base formula. What is the change of base formula? Can we quickly recollect? Suppose I have log to the base b of a, then it is equal to log to the log of a upon log of b. The top goes to top, the bottom goes to bottom. Just remember, this is a trick, and let the base can be anything. Obviously base should satisfy the condition c is greater than 0 and c is not equal to 1. Okay. This is the formula, that is a key principle that will help us in understanding this problem. Okay. Now let us take, if I take LHS, the problem is very simple, but you will miss out on some points. So let me start with RHS and let me try to simplify the problem. Okay. So I have RHS, which is log of 45 factorial to the base n. So it is log to the base n of 45 factorial. I have explained the notation. So this will be nothing but log to the base n of 45 into, let me write it this way, 44 and so on into 2 into 1. Okay. Now I have log to the same base, I have all the things multiplied together, right. So which rule will help me? It is multiplication rule that will help me. So if I use multiplication law, what does multiplication law states? If I have log to the base a of m into n, then this is equal to log to the base a of m plus log to the base a of n. Also all the conditions that are required for multiplication rule to satisfy are satisfied. You just check once, because it may lead to problems if you are not checking. For example, this n cannot be 1, we are assuming n cannot be 1, then I can apply the multiplication rule, and what will that multiplication rule yield? Log to the base n of 45 factorial is equal to log to the base n of 45 plus log to the base n of 44 plus and so on plus log to the base n of 2 plus log to the base n of 1. Okay. So if this is the case, can I write this in a smarter way? I can write it in terms of summation. So it will be r is equal to 1 to 45, because I have 1, 2, 3, 4 all these things. So I am writing in another way, log to the base n of r. Okay. So I roughly got the representation. Let us see what was the representation over here. Okay. 1 minute, let me slide down. Okay. Here I have the term in the denominator, right, and the summation starts from r is equal to 2. So these two features are missing so far. If you look at this term, these two features are missing. My r starts with 1 and I have only the numerator, denominator is divided by 1. So I want to do some adjustments, right. As we have already seen, the change of base formula will help, but I cannot blindly apply the change of base formula because r is 1, and if I apply change of base formula, then what will happen? Log to the base n of r is equal to 1 upon log to the base r of n. This is our change of base formula in special case. So I cannot blindly apply this formula. Why? Because my log is not defined. If r to the base n is equal to 1, r is equal to 1, my log is not defined. But if I use change of base formula, my r will be 1. So somehow I have to eliminate this r when r is equal to 1. So what is a term in this particular summation in this particular summation, that is contributing to r is equal to 1, this is the term, isn't it? If this is the term, we also know that log to any base of 1 is equal to 0. So, this property I will use, and therefore, I will have log to the base n of 1 is equal to 0. Therefore, I can write this summation as r is equal to 2 to 45. I hope this is clear, log to the base n of r. Okay. Now, I will apply this formula, change of base formula here, and this will be equal to summation over r is equal to 2 to 45 1 upon log to the base r of n, right. So, I got whatever I desired. So, this was my RHS, I started with this, I got my LHS, right. So, this is how I proved it. So, now let us come to the third problem. So, now the problem is slightly tricky. So, here you have been given n raised to 4 is less than 10 raised to n for fixed positive integer n which is greater than or equal to 2. Then show that n plus 1, obviously it should be raised to the power 4, and this is less than 10 raised to n plus 1. So, this is a question, how will you go about this? Now, first of all, it does not seem to be a logarithm question, but if you look at the location of this n and this n, you can guess that you can solve it using logarithm. So, what we have been given is, let us try to prove it. So, what we have been given, let me change the color of the marker, use a blue marker this time. I have been given n raised to 4 is less than 10 raised to n. Okay. So, if I want to convert this using the equivalence relation that we know from these terms and logarithm, log to some base n raised to 4 will be less than log to some base 10 raised to n. Now, I want to make the problem simple. So, what base shall I choose? Because this is 10 raised to n, it will be better for me if I choose the base 10. Why? It will be clear later. Then, if this is the case, then I can rewrite this as 4 times log to the base 10 of n less than n times log to the base 10 of 10. Okay. So, this is equivalent to saying this, isn't it? But now, log to the base a of a is always equal to 1. So, I have essentially simplified this as 4 times log to the base 10 of n is less than n. Okay. So, now you call this as some star or 1, whatever you want to call, let us call this as star. Okay. Now, what am I asked to show? This thing, right. So, how will I simplify this? So, let us take the ratio n plus 1 raised to 4 upon 10 raised to n plus 1. Okay. If you take this ratio, if I want to prove this, then it is equivalent to showing that this quantity is less than 1. This is to prove that. So if I want to prove this, then this is again equivalent to proving log to the base 10 of this entire quantity n plus 1 raised to 4 upon 10 raised to n plus 1 less than log to the base 10 of 1. What is log to the base 10 of 1? It's 0. So this is equivalent to saying log to the base 10 of n plus 1 raised to 4 upon 10 raised to n plus 1 less than 0. So I am essentially modifying what is to be proved. Okay. So let us now take the left hand side and try to prove that this quantity is less than 0. So first of all, if you look at terms of this kind, you will apply the division law or the quotient law, that is log to the base a of m by n, this n is different from this n, is equal to log to the base a of m minus log to the base a of n, isn't it? So I can apply that rule. I will take this term and I will say, let us call this as LHS. So LHS is equal to log to the base 10 of n plus 1 raised to 4 minus log to the base 10 of 10 raised to n plus 1, which is equivalent to saying 4 times log to the base 10 of n plus 1 minus n plus 1 times log to the base 10 of 10. You know something about this term is equal to 1. So I will use that, and I will use one more trick. 4 times log to the base 10. What I will do is I will take n common from this and I will take this as 1 plus 1 upon n. Why I am doing that will be clear very soon. Minus n plus 1. Okay. Again, if I have terms of this form, then I can apply the multiplication rule. So it's 4 times log to the base 10 of n. I am using the multiplication rule. So plus 4 times log to the base 10 of 1 plus 1 by n minus n minus 1. Right. I hope everything is clear till this point. But what do you know about this term? We have done something earlier, and that is a part of our given thing. I have marked some equation as star. You see this one. What is this? 4 times log to the base 10 of n is less than n. Can I introduce this inequality? Yes, because I want final result, I want to be less than 0. So I can introduce this. So this is less than n. So I can use the star and I can write here from star. I got this term to be less than n plus 4 times log to the base 10 of 1 plus 1 by n minus n minus 1. Okay. So this simplifies our calculation. What will happen now? This n gets cancelled with the other n, isn't it? Now I have not yet used the value that n is greater than or equal to 2. Can I use it now? So let us see. If n is greater than or equal to 2, what does this mean? This if and only if 1 by 2 is greater than or equal to 1 by n. Can I add on both sides 1? Yes, I can add. Therefore 1 plus 1 by 2 is greater than or equal to 1 plus 1 by n. If this condition, if this is satisfied, then what can I say about log? We have already seen several times. I can take log to any base, this relation will be satisfied. Do you all agree with me? If yes, then let us mark this equation as say double star or whatever this notation means. Then I am saying LHS is less than 4 times, let me not jump, first I will write that term, 4 times log to the base 10 of 1 plus 1 by n minus 1. Okay. Now I will use this expression, this I will call as double star, and from double star this quantity is again going to be less than or equal to 4 times log to the base 10 of 1 plus 1 by 2 minus 1, right. Okay. So this is again going to be equal to 4 times log to the base 10 of 3 by 2 minus 1. Now this minus 1 is creating problem. Is there any way of converting this minus 1 into a logarithmic term and then I can apply my power law or multiplication rule or quotient rule? Yes, there is a way. So first let us handle the first term, log to the base 10 of 3 by 2 raised to 4 is this term, minus log to the base 10 of 10 is 1. So this is fairly standard, now you must be acquainted with this. And now if I use my multiplication rule, power law, everything together and quotient rule, then what I will get is log to the base 10 of a number which is of the form 3 raised to 4, you know, 3 3s are 9, 9 into 9 is 81, upon 2 raised to 4, you know, is 16, and minus log to the base 10 of 10, I will apply the quotient rule. So this is into 10. So this is equal to log to the base 10 of 81 upon 160. Okay. Now I want to show that this term, if I want to show the result is true, this term should be less than 0. So the question now is this term less than 0? Let us simplify this term. This is equal to log to the base 10 of 81 minus log to the base 10 of 160. What do I know? I know something, the order relation between 81. 81 is less than 160. This if and only if log to any base, it doesn't matter, to the base 10 of 81 less than log to the base 10 of 160, right. So what will happen to this term? Log to the base 10 of 81 minus log to the base of 10 of 160 will be less than 0, correct. This is what we wanted. So again let us go back what we did so far. Okay. So we were given n raised to 4 less than 10 raised to n for a fixed positive number. Remember this condition is crucial, n is greater than or equal to 2, and we had to show that n plus 1 is less than 10 raised to n plus 1. Apparently this problem was looking like it doesn't involve log, but because of this base and power we made log as a easiest tool for solving this problem. So what we did first given such a problem, you first identify, you bring all n's in one line, like here we did n raised to 4 less than 10 raised to n, then we brought log in this form and we made n in one level at one level. Then we designed how to change the to prove that factor. So to prove that is this, again we use log and simplified the term. Using the power of log, it suffices to prove that log of some term is less than 0. Then we started with that term as LHS and tried to prove this term is less than log, this term is less than 0. So in order to do that, we use the order relation that that is there in the log, and that is what this is. Okay. So this helps a lot in solving many problems which are in the exponent form or which are in general exponent and power form. Okay. Now let us try to do somewhat difficult problem. We have solved a similar problem, but this is more general. So let me choose the red color now. I think this is the fourth problem that I will be doing. It's a fourth problem. This is a fourth problem. If you remember, we have done similar problem, but not exactly similar. Log of x upon y minus z is equal to log of y upon z minus x, which is also equal to log of z upon x minus y. This is the relation that it satisfies, and then I have to prove that, show that x raised to y plus z plus y raised to z plus x plus z raised to x plus y is greater than or equal to 3. Okay. So if you look at this problem carefully, this is somewhat like ratio proportion problem. So I can simplify this in this way. I can simplify this in a way like I can write this log this ratio. I will rewrite this log. Let us assume this is to the base a. The base actually does not matter as long as it is not 1. Y minus z is equal to log to the base a of y upon z minus x, which is equal to log to the base a of z upon x minus y. Let us put this is equal to some k. Okay. Then what do I know? I know something like this. Log to the base a of x is nothing but k times y minus z. Also I know log to the base a of y is k times z minus x. Log to the base a of z is equal to k times x minus y. Okay. Fine. Now what do we want? We want to prove this thing. If you look at this term x raised to y plus z, then I have similar term over here which is y minus z. So if I convert this logarithmic expression into the expression that is x is equal to something, then I may get something. So let me guess it. So if this is the expression, then this has a equivalent exponential form, which is x is equal to a raised to k times y minus z. Similar thing is true with this expression, y is equal to a raised to k times z minus x. Similarly, z is equal to a raised to k times x minus y. Now I will feed all these equations, all these expressions into this expression. What do I get? So I am using log and exponential equivalence relation, and let me feed it here. So I have a raised to k times, if I substitute y minus z, it will be multiplied by, okay, let me go slow, y minus z into y plus z plus a raised to k times z minus x into z plus x plus a raised to k times x minus y into x plus y. Okay, I am not writing the other side, but this is equivalent to saying this is equal to a raised to k times y square minus z square plus a raised to k times z square minus x square plus a raised to k times x square minus y square. Okay. So now after this we cannot use log in a straightforward manner. So we have to do some trick. So if I look at this term, then this term is greater than or equal to 3. That means we are actually taking on an average the term, every term is greater than or equal to 1. So what I can do is I can divide this term by 3. Okay. So I will just multiply all the terms by 1 by 3. So this is 1 by 3. But what exactly is this? This is nothing but arithmetic average of these 3 terms. Okay. If this is the case, then I can use the formula that arithmetic average is always greater than or equal to geometric average. Why I am doing this? Because I want to use the power of log. So using this relation, I can say that this is greater than or equal to, what will be the geometric average corresponding to this term into this term into this term raised to 1 by 3. Then I will get this as a raised to k times y square minus z square into a raised to k times z square minus x square into a raised to k times x square minus y square, the whole thing raised to 1 upon 3. Okay. Okay. But now something is happening. Now you can see this is nothing but a raised to m, a raised to n, a raised to r. So it is a raised to m plus n plus r. So therefore it is a raised to k will be common, y square minus z square plus z square minus x square plus x square minus y square raised to 1 by 3. What will this be? Y square getting cancelled with y square, z square, x square, x square. Okay. So this is a raised to 0, which is 1. So this is equal to 1. Okay. So what we have proved now? 1 by 3. So what we have proved is 1 by 3 times x raised to y plus z plus y raised to z plus x, that is what it is, plus z raised to x plus y is greater than or equal to 1, and therefore we have proved our result. Because you multiply by 3, you will get this inequality. Okay. So let us take the next problem, which is very interesting because we are combining the knowledge of trigonometry and log together. So it is log to the base 0.1 of sine 2x. So now the argument is sine 2x plus log to the base 10, argument is cos x. This is equal to log to the base 10 of 7. This is given and you have to solve this expression for legitimate values of x. solve for x. How will you solve this expression? We have to make certain observations. First of all, this expression has a base 10 in two terms, and in one term it has a base 0.1. So, I cannot use my multiplication rule, product rule, division rule, anything. So, first of all I have to convert this base to base 10. So, let us isolate this. Log to the base 0.1 of sin 2x is equal to log to the base of 10 inverse sin 2x. Then I will use my formula or the rule, log of b raised to m a is equal to 1 upon m log to the base b of a. So, therefore, I will have minus 1 into log to the base 10 of sin 2x. Okay. So, now I will substitute this expression into this in place of this. So, my expression now becomes, then I will rearrange. So, because this has a positive sign, I will write this expression in the first, log to the base 10 of cos x minus log to the base 10 of sin 2x is nothing but equal to log to the base 10 of 7. This is given to us. Now, I can use the quotient rule and say that this is equivalent to saying log to the base 10 of cos x upon sin 2x, very simple, which is equal to log to the base 10 of 7. Okay. Now, I know two terms are equal in the log. So, I also know cos x upon sin 2x is equal to 7. This is if and only if, right. But I know some formula for sin 2x also. What is formula for sin 2x? 2 sin x cos x. So, I will use that formula, 2 sin x cos x is equal to 7. Cos x gets cancelled. Therefore, I got 1 upon sin x is equal to 14, that is sin x is equal to 1 upon 14. Now, you have to be little bit careful. The question is solve for x. So, you have to find all values of x. So, if you can easily say x is equal to sin inverse of 1 upon 14 is one of the values, but this is not the only one value. Then what are the possible values? If you are aware of trigonometric function, all values of the form n pi plus minus 1 raised to n sin, again this one, sin inverse of 1 upon 14. Why this is true? Because sin is a periodic function. So, sin x is equal to 1 by 14 after every n pi values, only thing is its sign will change, that is what is represented by this minus 1 raised to n. Okay. But will these values satisfy our equation? What is our equation? Our equation is a logarithmic equation, right. So, if I want to define this equation, then I need to ensure that sin 2x must be greater than 0, cos x must be greater than 0. So, this is a general solution, but this is not the final solution. I need to ensure sin 2x must be greater than 0 and cos x must be greater than 0, right, in order the log to be defined. If cos x is greater than 0, then sin 2x is nothing but 2 sin x cos x, which we have already used. So, this also forces sin x all the time must be greater than 0 and cos x must be greater than 0, right. When will this happen? This will happen only when x lies in the first quadrant, x is the angle which lies in the first, if it lies in the first quadrant, this will happen, right. So, if x lies in the first quadrant, then what should be the value of n over here? This always should be even because it lies in the first quadrant. So, this minus 1 raised to n vanishes, and therefore, the value of x must be equal to, because this is even, I will write this as 2m pi plus sine inverse of 1 by 14. See, this is how you should be careful while solving the problem. So, we have almost eliminated half of the values for x, which we have said okay earlier. So, this is the answer, this is the correct answer. So, just be careful when it is merged with trigonometric functions, you have to see whether these things make sense. If it is 0, then also there is a problem. So, you have to eliminate all those values. Okay. So, let us now try to solve one more trigonometric problem, so that it will be more clear in your mind. Okay. This time I will introduce more complication. I will introduce trigonometric function in the base. So, it is log of sin x with base cos x. Okay. Another thing is log of, obviously you can guess, then I will write here log of cos x with base sin x, and this is equal to 2, and I will solve for all values of x. So, this is the twist now. Now, it is in the base. So, if something is in the base, what are the conditions? So, if a is the base, a should be greater than 0 and a cannot be equal to 1. This is the trick. Okay. Now, I cannot work with these values in the base. So, what I will do is I will use change of base and I will try to simplify this. So, you can take any base, but it does not matter. Okay, let me, something happened, so let me zoom it. Okay. So, it is log of sin x with some base a, log of cos x, I am using change of base. So, let it be some base a plus log of cos x upon log of sin x, let it be some base a, this is equal to 2. Okay. Now, if I simplify this, what I get is log of sin x the whole square. So, I am just simplifying, I am taking the LCM of the denominator and simplifying it, putting it on the other side, and you must be expert in this particular computation. Minus 2 times log to the base a of cos x into log to the base a of sin x is equal to 0 obviously. What is this? This is nothing but log to the base a sin x minus log to the base a of cos x the whole square is equal to 0. That means, log to the base a of sin x must be equal to log to the base a of cos x. We have done it several times. That means what? That means sin x, this is true if and only if sin x is equal to cos x. Again this is true if and only if sin x upon cos x is equal to 1, that is nothing but tan x is equal to 1. Again tan is a periodic function. So, x is equal to tan inverse of 1, which is pi by 4 is one value, but how many times it will happen, right. So, it will happen after every pi rotation. So, it is n pi, right. So, let us call this equation as star. So, we have figured out all possible values of x for which tan x is equal to 1, but does that satisfy our logarithmic expression? That is something that we need to check. This is a very important thing. So, in order to satisfy this logarithmic equation, what are the things that are needed? Sin x cannot be 0, sin x cannot be 1, cos x cannot be 0, cos x cannot be 1, because cos x cannot be 1 because it is in the base, sin x cannot be 1 because it is in the base, it cannot be 0 because it is in the argument also. Okay. So, let us list these things. Sin x not equal to 1, cos x not equal to 1. Also, I need sin x to be greater than 0, cos x also should be greater than 0, it cannot be 0. So, again this forces me to say that my x should lie in the first quadrant, isn't it, and it cannot take any value of the form x cannot be equal to n pi plus minus 1 raised to n pi by 4 pi by 2, and it cannot take any value which is of this form 2n pi. Why? Because in this case our cos our sin x will be 0. So, these are the values that are not possible. So, what are the values we are left with? X is equal to, again it should be in the first quadrant. So, it should be a multiple, even multiple of pi, and naturally it is of the form pi by 4. So, these are the only values that are possible. Okay, that is all about the problems. So, let us summarize the topic of logarithms. In the beginning we started with introduction of logarithm. We have seen that logarithm and exponential forms are in one-to-one correspondence with each other. That gives us the 7th rule, in which we will convert the logarithmic form into exponential form. This was the beginning. Then in the first lecture what we have seen is how to evaluate the logarithm given the base and the number. Once you can evaluate the logarithm, you can actually go into more detail, and we have seen that there are some laws of logarithms. In particular, we have seen multiplication law, we have seen quotient law, we have seen power law, we have seen change of base law. These 4 are typically crucial laws which you should always remember, and from that we have done some important deductions. Okay. What multiplication law is doing? Multiplication law is actually converting a multiplication of 2 numbers with respect to log into addition of 2 numbers with respect to log, provided they satisfy the conditions. Now, this should be your second nature. What should be the conditions? The base should be greater than 0, the number should be greater than 0, and the base cannot be equal to 1. If these 3 conditions are satisfied, then your logarithm is well defined. We have seen through several problems that if one of the conditions is violated, then some of the solutions can be excluded, right. So, whenever you are solving a problem on logarithm, you should always resubstitute the values or the solutions that you have got as a solution of the problem, and then check whether they really satisfy the expression or the expression stays meaningful after you resubstitute those values. Okay. So, these are some important checks that you have to do. Another important thing that we have seen is most of the complications in your general problems like trigonometric problems or quadratic problems can be introduced via logarithms. So, though logarithm is not a separate topic in your syllabus, but logarithm can play a crucial role for introducing complications. So, you should solve many problems in logarithms in order to gain mastery over the topic of logarithms.